Hello, A-level students, GCSE, IB, AP Physics, interested person, whatever you are. Welcome back to our channel. Today we're going to embark on a cosmic journey to explore the fascinating lifestyle of stars, particularly those in mass, which is very similar to that of our sun. So we're going to go through the life cycle of those, which we would call medium or low mass stars, and in another video we can talk about the fates of stars which are of a much greater mass. So stars, like living beings, have a life cycle, and the story begins with a cloud of gas and dust called a nebula. Here we have the very famous nebula, the pillars of creation, which I believe in terms of their height there are like 2 light years in height. So very, very large, very, very cold. So just above absolute zero, maybe 10 Kelvin or something like that. Clouds of gas, primarily, your most fundamental gas you can get. So this is primarily just clouds of hydrogen. Within this cosmic cloud, the gravity, starts to begin to pull the gas and dust together. So that's a process that's going to happen over, tens, hundred thousands of years, forming what we call a protostar, right? So that gas will start to group together as a process of the gravitational attraction, and we will refer to that as a protostar, the thing that comes before a star, much like a prototype, if you kind of go into the etymology of the word there. As the protostar continues to gather mass, okay, as more and more of that cloud of gas starts to come together into one point, its core heats up and nuclear fusion ignites. And voila, at that point we have a star, right? At that point, the star enters what we call the main sequence phase, where it remains stable for the most of its life, okay? So here we've got our main sequence star. That is the stage which our sun is in at the moment, and it's because that core was able to ignite and allow the process of nuclear fusion to take place, right? So for nuclear fusion to take place, you need very, very high temperatures and you need very, very high pressures. So that pressure is going to come as a consequence of the density being, increased because of all that gas getting closer together. Now, why do we need that high temperature and that high density and the pressures that come with it to result in stable, continuous nuclear fusion? Well, for our hydrogens to fuse into helium, they require those two nuclei to get close enough to each other for them to be bound and joined together by the strong nuclear force. Now, the strong nuclear force has a very, very small range, but it's incredibly powerful. So if we get those nuclei close enough, the strong nuclear force can take over, and as hydrogen can fuse into helium. Helium, of course, having a higher binding energy than that of hydrogen. So the excess energy, the mass deficit, that is released as energy, and that is, the electromagnetic spectrum range of energy of radiation that's being released in the sun as a black body radiator. Okay? So we need those high pressures, we need those high temperatures so they can get close enough, because what's stopping them from getting close enough is the electrostatic forces of repulsion that's going to take place due to those two positive nuclei repelling each other, right? So to overcome that electrostatic force of repulsion, we need that high temperature, we need that high density, which is going to give us pressure, because that high temperature and that high pressure is going to increase the kinetic energy of the gas. The increased kinetic energy of the gas is going to give us more collisions, it's going to give us harder collisions, and they are going to be frequent and strong enough to overcome that electrostatic force of repulsion and to result in nuclear fusion. So during this phase, Stars like our sun shine brightly as they're converting that hydrogen into helium through that process of nuclear fusion. And this process generates energy, as I said. That excess energy from the fusion is released, okay? Which counteracts the weight of the star itself, kind of like we can see in this diagram here. So we end up with a state of equilibrium. It's kind of like a balloon, right? A balloon maintains a stable shape because the outward pressure, right, from the gas that you have colliding around inside the balloon is equal to that of the atmospheric pressure, which is acting inwards, right? So what we have here is the energy released is providing enough force to counteract the weight acting inwards, and that's why we end up with this stable main sequence star. The sun isn't changing size every day, right? Because it's maintaining, this nice steady rate of constant nuclear fusion. Its weight's basically staying the same, and so we have that, nice big spherical ball. It's a delicate balance, though, right? Because that weight is trying to collapse the star. And like all good things, the main sequence phase must come to an end. When a star like our sun starts to exhaust its hydrogen fuel and it's moving up to larger and larger elements in the periodic table, the rate of fusion is going to decrease, right? Because we're going to need more pressure, we're going to need more temperature to overcome these larger electrostatic forces of repulsion. Right? So the rate of fusion is going to decrease. The energy that's released in these fusions is less. We'll have a look at that when we look at a nucleon per energy binding curve in another video. But as a consequence of these things, the energy being released decreases, the rate of fusion decreases, the weight's basically staying the same. So the star collapses in on itself and it enters a new stage of its life cycle, the red giant phase. So during the red giant phase, the star swells up, becoming larger and cooler. Despite its name, the star's surface actually cools down, giving this reddish hue, as opposed to the white that it started off before. The phase can be quite dramatic, with the star shedding its outer layers into outer space, forming a beautiful nebula. Now, this is a nebula made up of the more complex elements that were fused by the main sequence star. This is a planetary nebula. So these are elements that could very well come together to create a new planet, moon, natural satellite, whatever, right? And after this grand spectacle, yeah, we're going to go through the same process again. Okay? So stars reach another critical point here in its life cycle, the formation of the planetary nebula, and this is really sort of marking an end, the beginning of the end for stars like our sun on that sort of scale. So that planetary nebula that's been shed by the collapse of the red giant will eventually drift away, and we will be left with a hot, dense core called a white dwarf. And the white dwarf is something that is going to gradually cool down over billions of years, eventually fading into a dark, cold remnant known as a black dwarf or a brown dwarf, right? So the white dwarf here is not undergoing active fusion, okay? It's simply a result of the red giant collapsing and shedding its planetary nebula. And that hot core that was left from the red giant is now just cooling down. So it's very small but very bright, okay? And it'll take billions of years for it to cool down. The way I think about it is like imagine you've got like a barbecue or something like that, and you've got like the hot coal that's left over that's cooling down. That's the white dwarf. It's the hot coal. It's the hot core that is cooling over. And really, there you have it. A-level students, IB, whoever you are, the life cycle of stars in mass similar to our sun from birth to death. Okay, it's like a cosmic journey that spans billions of years. And for me, it's one that leaves me kind of in awe. of the wonders of the universe, because I start thinking about, whoa, cloud of gas comes together, dense enough to overcome the electrostatic forces of repulsion, fuses, stable fusion for a long time, rate of fusion decreases, collapses, expands into the red giant, continue to fuse, again, rate of fusion decreases, collapses, sheds a planetary nebula. Whoa, that's where all this came from, right? Left over with that white dwarf for billions of years, which is cooling down until eventually it's a brown dwarf, black dwarf, whatever you want to call it. So thank you for joining us today. Don't forget to like, share, and subscribe for more, in this case, cosmic content. Keep looking up and check out the stars in the sky, because if you kind of like put to perspective this sort of stuff, I don't know, it's kind of wild. Stick around at the moment if you want to hear about other places you can reach me, but if not, feel free to run away. So thank you for those who stopped by. Your interest and support mean a lot to me. If there's any questions or further assistance you would like, feel free to reach out, whether you're a teacher, whether you're a student, whatever, whether you're somebody who's just interested in this sort of stuff. Comments below, easy way to reach me. And I've got a bunch of links over here, which are in the description again, if you care. My link tree's there. YouTube channel, you're already on it. I've got physics resources over on that page there. Twitter, I'm starting to post a little bit more there. Instagram, if you're feeling generous and you want to buy me a coffee, there is a link there. But there's no expectation of any of this sort of stuff. I just want to educate you. Thank you again. Again, comment, direct me what sort of things you would like to see, and I will catch you all a little bit later. Bye, bye, bye.